Welcome to the Ontology Summit 2021. I'm very pleased to introduce Mike Bennett, who is going to be speaking today as part of the Track A, the ontological landscape. And today is March 3rd, 2021. So Mike, go ahead.
Thanks, Ken. Hi, everybody. So today I said I would introduce some thoughts about different styles of ontology. This very much complements some slides that you saw in a previous session from Todd Schneider and various other things out there on the idea that there are different kinds of ontology for different purposes and what the different desirable design characteristics might be for those, the do's and don'ts for them. So I start right back with basic principles, which is what I call the dimensions of a model. So typically we pick up a modeling language like UML or OWL or something and just kind of assume that what it's for and how it represents things and so on is all tied together. And in some languages, they pretty much follow each other, but it's helpful to separate out what is it that the model is a model of. So the model reference dimension, the semiotics, if you like. So is it a model of data? Is it a model of real things like trees and houses and people? Is it a model of computational stuff or whatever? Separate from what is the formalism, i.e., is it using formal logic? Is it using object orientation formalism? And so on. And this can apply to any kind of model at all, anything from UML model to a sheet of music, for example, or anything else. And then separately to that, although it often follows as to what are the most ideal or non-ideal choices for formalism and representation, is what is it you're using it for? Is it a model to drive the design of some solution? Is it a model to describe the problem space in some way, and so on? So ontologies fit into that in various ways. Typically, we think of an ontology as being a model of real things in the world. So the model reference dimension is the things. We often say things versus strings. But sometimes, even when we say we're doing that, we find that what we're really thinking of is data about the things, what you might call digital twins, for example. And often you can be talking to somebody thinking they're talking about the things, and actually in their head is always the data. And that's not wrong, it's just different. What is it as a model of, and what formalism you use, and you can use formalisms like OWL to do either of those things, and it may be more or less ideal for some applications versus others. So let's look at some basic development principles. We have this idea of what we call the separation of concerns. So you have things like a logical model, that's a platform independent model, so it embodies a design. So for example, that might be the design of some software, and then the implementation would be in Java or C++ or something, or it could be the logical design of a database, so a database schema which might be implemented in several different physical database formats. And separate from that is the conceptual model, and these initials here stand for computationally independent model, as distinct from the platform independent model and the platform specific model. So as the name suggests, that's computationally independent. Now, a lot of people assume when they see these that to talk about the separation of concerns is to talk about waterfall. And in the waterfall method, you always finish one of these things and sign it off before starting to work on the next thing. So you finish a requirement specification, for example, or a set of use cases or requirements catalog, and then realize that in the design of some solution and then implement that. But it doesn't follow just because of those concerns are separated that they have to be done in order. So more flexible development methodologies like the rational unified process and others that we've seen over the years would scrunch these together, so you start to realize elements of your design as soon as you have some initial core of your conceptual model, and you extend and develop those more or less in parallel. So the separation of concerns is independent of any methodology that you use. What it is about is separating not only logical from physical design, but also separating the language of business and technology, so what I call the language interface, that a computationally independent model should be in the language of the business. It's a formally controlled artifact. It should have formal version control and change management and so on, but it should not presume anything about the design, and it should not require any understanding of the language of design in order to validate and sign that off. And that's true whether it's a set of requirements for the behavior of a program or a set of concepts for what goes into some data model. The same thinking applies whether we're looking at the behavioral or what we call the structural or data side of things. And so in some methodology, you can then iterate between those as you realize and extend each of those artifacts until you get to the end of the project. The thing to keep in mind about this, and here we talk about the data or structural side of it, the computationally independent model is an ontology. I'm going to qualify that by calling it a conceptual ontology. Sometimes we call it a concept ontology to avoid confusion. I'll explain why in a second. Then you have a logical data model and a physical data model for typical database design and so on. Now, a lot of people think, oh, I'm going to create a conceptual model for the business, so I'm going to take my logical model and I'm going to cross out all the complicated bits, things like interest rates and dates and so on, as though the IT domain somehow owns all that complexity. Now, they certainly own some complexity in the way the design has been thought about and implemented, but there's just as much complexity in the business domain. If somebody in, say, you've got a set of payment terms with interest rates and payment dates and interest accrual basis and so on, a lot of people make the mistake of thinking, well, that's all very complicated stuff, so it must belong to IT. It's part of our data model. Now we'll show that data model back to the business people, but cross out all the complicated bits. But actually, all of those same terms about accrual basis and interest rates and so on, they belong to the business. They sit on term sheets where they are the properties of some formal commitment by one business to another. So the true conceptual ontology is not like a conceptual data model, like what a lot of people call a conceptual model. It's not an abstraction of the solution. You're not taking something you've already designed from the bottom up and presenting it back to business. Rather, it's a concrete model of the problem space, or we could say more accurately, a concrete model of the conceptualization of that problem space as the business conceptualizes it. So that's the key thing about this kind of computationally independent ontology artifact. So now we can think about, well, is that all ontologies are? Are there different ontologies for design versus concept and so on? So here's something that I wanted to think about. If you take a conceptual ontology in, say, the web ontology language, OWL, and you have an operational ontology for some particular application use case, you might extract and optimize different subsets of your conceptual ontology according to the context of that use case. That's all well and good. But if your conceptual ontology has data type properties, it has OWL data types, well, those are platform specific matter. You notice we've lost the logical step in the middle there for now. What happens if you have an OWL-based conceptual ontology that has data type properties, which most of them do? Well, that's making a computational commitment, maybe a very simple commitment to computational data types, but it's not really a conceptual model. It may be conceptual in one broader sense in that it does represent business concepts, but it represents those business concepts as expressed in data. So there's the distinction between the real things and the data, and most real things do not get their definition from data. That sounds obvious, but if you tend to work in that bottom-up way where you start with some OWL application ontology and start showing it around to the business later, it's likely you're making data decisions, design decisions, that you're then propagating back to your computationally independent model to the business, which, according to the rules, should not embody any design decisions. So there's a couple of different styles that you tend to see that will tell you whether or not the kind of thing you're seeing is a computational application ontology or a computationally independent representation of things in the world. So without wanting to go into all the details of this model, it looks complex, but it's a thing I use in my training courses where we get people to look at what's the meaning of quay, jetty, wharf and pier, and they're defined basically by two of those things out of the four are parallel to the shore, and two of them are perpendicular, two of them have open pilings, and two of them are solid. So you have this kind of conceptualization as you roll up the common concepts, and you can roll it all the way up to landing structure, which is a kind of built thing, and ultimately that's a kind of thing, and your orientation and construction and so on. And you have these very high level abstractions like direction and geographical feature and method, of which construction method is a kind. That's a lot of abstraction that you don't want to see in an application. If you're designing an ontology application, you want something more like this, where you just have the stuff relevant to your use case. You have landing structures, you have orientation, and you have construction, and that's it. And notice, and this is the clue to look for, you have properties here with no domain and range. You have has construction, has orientation. That's exactly what you need in an application ontology, but clearly those properties don't really convey much in the way of business meaning. They are just a property of a thing defined in terms of a thing. Whereas if we go back to our previous one, you'll see that by having these abstractions, we're able to say something more definite about the properties, what kind of thing they can be a property of, and what kind of thing they're defined in terms of. And sometimes that's still thing, but not often. So that kind of distinction is there. And then there's the question about data, which I want to dive into a little bit more. So the real issue is this, for maybe 90% of the time, maybe 99% of the time for some business areas, there's not a lot of difference between the business stuff and the data stuff. So if you have a term sheet for a financial instrument and it has those interest rates and accrual basis and payment amounts and dates and things like that, they all look exactly the same in data as they are in the business reality of a term sheet, which is written out typically in words, but very formally defined words. And so that's a fairly lossless difference. And for a lot of the time, you can then pretend that there is no difference and that the data is the things. But actually, you've made a decision already that you're using the data as surrogates for the things. So actually, we want to step back and say, well, for our computationally independent ontology, we're trying to model what things really are. We've said things versus strings, and then we've often tried to smuggle in the strings. But what are the things? What does it mean to be a thing? So typically what we do in ontology is we have a class, so a category or a set of things in the world, and an intentional description, a logical description of what it takes to be a member of that set of things. So that's what we call truth makers, or in Aristotelian terms, the differentiae. What are the necessary and sufficient conditions that an individual thing in the world has to have in order to be a member of that set of things? And that's what we mean when we say, what does it mean to be that thing? Now, those truth makers are mostly not made of data. Things get their real world meaning from legal capacities, laws, accounting concepts, biology, physics, whatever the things really are. That's the thing, the terms in which our truth makers are stated. Separately, we can say, well, given a particular truth maker, what data is available about that thing or its distinguishing properties? And sometimes there's no data directly available that reflects a real world truth maker. Sometimes there may be a sort of a fingerprint. So I'll dig into that a little bit more in a moment. Then, of course, there's also the question of data typing. You've got kinds of information in the world. They may or may not be reflected in computational data types. So you've got data typing decisions to make in any application, whether it's an operational ontology or a database or something else. So those are design decisions again. And there are a few things in the world that originate only in data, like formally published identifiers for certain things. If it originates in a computer and it's real, then fine. But for everything else, you're taking something in the world and finding the closest, most useful data type to represent that. So what we're doing with ontology is we're defining the world of things. We're defining types of things in terms of set specifications. I borrowed this table from Jim Logan of No Magic. You have sets of things that correspond to those types. So here's the set of all things that are towers. They are the intersection of tall, narrow, and structure things. And you have individual members of that set, such as the Eiffel Tower. An ontology of things would just tell you that. Separately, you may have some information construct, some data. So you've got a set specification for membership of the class of data about that thing. You have one of many sets of record structures that contain observations. This is particularly important with something like the Internet of Things, where you actually may often need to have an ontology that distinguishes not only the thing that we're measuring, but the measurements of the thing, as those are two different matters. And then you may have at the individual level the member of some set of observations, such as hash tower 123, the member of the set of observations about towers. So the information is not the things. So I'm talking about truth makers. What does it mean to be a thing? Here's a fairly simple model of what it means to be a loan. Strictly speaking, this would be what it means to be a bank loan, I should say. But you have a loan contract, you have the loan drawdown. That's the actual matter of drawing down a sum of money on a particular date under the terms defined in the contract. The contract has terms like terms of the payment of interest and repayment of principal. It typically has securitization terms such as collateral, and it has the parties, the borrower and the lender, and sometimes some third parties. Now, what it also has is something called a credit facility. A bank won't lend you money unless they've defined a credit facility. Now, in some specialist cases, that credit facility may itself have a contract, for example, for a home equity line of credit or a credit card or a construction loan. In other cases, when you go to the bank, they take a lot of trouble not to tell you how much they would lend you for particular purposes. They have tranches of these credit facilities. So part of the meaning of that kind of bank loan is that it has a credit facility. That's what we might call a truth maker. It is true of a bank loan that it's only drawn down against some credit facility, but we might not care about that for a particular application that we're doing, or even for a whole range of applications that we're doing an ontology for. We might never care about modeling those credit facilities. That doesn't mean that the credit facility isn't a fact about what it takes to be a kind of loan. So the truth makers may or may not exist in data. Sometimes there may be things that we define that there's no corresponding data for at all. So you may not need the data in order to deal with that. The data you need and need to reason over in operational ontologies may or may not have anything to do with what it means to be a given category of thing. So if you're modeling the meaning of something, you're going to be looking at different features. You're going to be looking at the necessary and sufficient conditions to be that class of thing. Whereas if you're processing data about something, you're looking at what data do I have? What competency questions do I wish to address with my application ontology? And how do I use that data to draw conclusions from the data I have to new data that I need? So data is not semantics. And if you're integrating across multiple sources, or if you're scraping text and doing AI and natural language processing, or if you're drawing inferences about things that are not natively in the data, then you may actually want to know more about the truth makers of a thing, even if you don't have data for that. Because what you may then want to do is look for these digital fingerprints I mentioned. Let's see if I've got an example here. I'll skip ahead. No. For most of the time, there's going to be data that directly reflects the things. We could call that a data surrogate, for example. In many cases, we use the word digital twins, particularly for data that can be used as a whole, as a surrogate for a thing as a whole. So the digital twin of a person, or digital twins of IoT devices and so on. And there may be data that directly reflects the properties that make something a kind of thing. So if you have a payment commitment and it has an interest rate and a interest accrual date and all of those things, you could reason over that and say, well, I've got enough data to tell me that that is a interest payment commitment, for example. But other times they might not. So one example, for to be a bank, what does it mean to be a bank? So a bank is an institution that is legally able to take in funds and disperse funds, and it is legally allowed to do so in the basis where it borrows short and lends long. And there's all those real world truth makers based around legal capacities, organizational capabilities, things like that, which mostly aren't in the data at all. But what is in the data would be a banking license. And so at least in a Western economy, an established economy, you have a banking license that's issued by the relevant authorities that is always present when all those social and legal capacities are there, and always absent when it's not. So there was one project I worked on a while ago where somebody wanted to define what a bank is, and they decided to use something called FDIC insurance. That's a particularly US federal insurance policy, because all banks had FDIC insurance. Now, straight away, you can see one problem with that, which is that, excuse me, that not all banks are insured in the United States of America. The other more subtle problem was that the Depository Trust and Clearing Corporation, DTCC, has FDIC insurance and is not a bank. So by instinctively taking a piece of data and not asking themselves what is the best data to provide a digital fingerprint or an indication of the presence of those legal capacities, they chose the wrong data surrogate. Once they realized that, they then replaced it with the data surrogate of banking license. Now, for a different application, you might want to reason over stuff in some new economy space like blockchain or in some emerging market, and detect when somebody's acting as a bank without having a banking license. So then you're going to need different digital surrogates to try and find what they're doing that corresponds to and possibly breaks the law about particular legal capacities. Likewise, legal personhood is defined by something having the capacity to incur debt and be sued at law. You won't typically find a piece of data about that, but you'll often find pieces of data such as, if the legal person is not a human, their existence in some company registry that shows that they have been incorporated as a kind of legal person under the laws of some jurisdiction. That gives you a good data surrogate for the real world truth maker of having the legal capacity to incur debt and be sued on law. Sometimes we may not have any of that, and we simply have, and you'll see this a lot in ontologies, a taxonomic hierarchy of classes without any differentiating properties, just some definition. And what we're effectively doing then is we're grounding the meaning externally in those definitions, and ideally with some metadata pointing to a written source of those definitions. So that's kind of where the meaning gets in, if you like, in the absence of having either data representations of the real world truth makers or digital fingerprints that reliably correspond to those. So that's one kind of decision you have to think about in getting from an ontology about things to an ontology about strings. The other thing is, in the real world, there are kinds of information. If you ask a business person, does this thing have a yes or no answer? They might say for some things, well, it has yes, no, and maybe. Well, there's nothing like Boolean for yes, no, and maybe. So you have to design something around that, like an enumeration of 3 states or something. You may have days and dates and times. Sometimes you can say of a particular thing it has to happen on a day, but that day may be defined as 3 days after the day of this other thing happening. It may not be a date data type. Other times it will be. Phone numbers, textual stuff, names, all kinds of information, controlled lists, numbers. So mathematicians will understand all sorts of things like real numbers, rational numbers. I haven't included some of these in the list now, but I've been reading up on this recently. All these kinds of number, those don't necessarily directly correspond to data types. Often they do. And then you have URLs, hashes for blockchain and stuff, binary stuff like pictures and other media, all kinds of information. Then you have data types. That's a lot simpler because you're making design decisions. How am I going to represent that thing in the world, including that thing that is information, like a name, should I simply use text for a name, or do I need some ontological breakdown of family name, given name, and so on? Do I want restricted or unrestricted text? You have date and date time, you have Boolean, but no, yes, no, maybe. You have formal enumerations, and depending on your typing scheme, you may have several different kinds of numeric, like integers, floats, non-negative integers, positive integers, and so on. URIs, of course, and for the binaries, you have different file formats and stuff. And in OWL, you may have noticed, if you're familiar with OWL, not all of these are possible. There are some data types you can't do. So the data types are a commitment to some computational usage. So if I give somebody my phone number, that's the kind of information. It looks like a number. I'm sure you've all had the thing where you stick that in a spreadsheet and it rips off the leading zero, because the spreadsheet is quite sure that what you typed in as a phone number should be a number. Of course, it's not. It's text. It's text in which the characters are restricted to the digits, but it's still text. So those decisions sometimes are made for you, and when it goes wrong, it gets interesting. So let's go back to our conceptual, logical, and physical language interface now. You have, in the conceptual world, you can model things in formal logic, such as description logic. Of course, higher orders of logic are needed to say more complex things about the world. Let's stick with DL for now. Now you can serialize that in OWL. What you have then is an OWL serialization of a DL model. You can make that your conceptual model. You'll see that the style of OWL, I showed you earlier, when you have, high levels of abstraction and lots of property domains and ranges and so on, things like that might get you in trouble if you try and use that OWL directly for a physical application for answering specific competency questions over a particular set of instance data. It's not for that. And so some people get confused. If you serialize your DL in OWL, they think, oh, you're doing it wrong because here's all the rules I would use for my operational ontology. But also, straight away with that OWL, it should have no data type properties, or very few, only for the things that originate in a computer as a real thing, such as a formal identifier that's in numbers or alphanumeric or something. So you're going to do some design activity. You're going to derive from that something which is roughly equivalent to a logical model, effectively, because it would be something very like your conceptual ontology, but with data types. So you would replace some of those information kinds with RDF-OWL data types. And by the way, the subset of XML you're allowed to use, you can't use date as a data type. You can only use date time because of reasoning reasons. You can't use extended data types like G month day to talk about the 28th day of every month or something, much as you might have wanted to use that for a conceptual data model. So you put in those data types for your information kinds, you identify any data surrogates for particular truth makers and any digital fingerprints where the truth maker isn't directly reflecting the data, but there's some clue that the real thing is there, like the banking license, for example. And now you can stand up RDF instance data on that. You can put it in an enterprise triple store and enterprise knowledge graph to have a common conceptual ontology to use right across the organization. You probably wouldn't want to use that in individual applications. It gets a bit too big and clunky. It will have all those high-level abstractions that, it'll have lots of property domain and ranges. It'll have lots of top-level ontology stuff like parties and roles and various temporal treatments like past, present, and future. You don't want most of that in any individual operational ontology. You want to flatten that. You want to replace some of those relative things like parties and roles with independent things, have a direct relationship from, say, a loan to a borrower, rather than an indirect relationship to loan to borrower to person. You go direct to loan is borrowed by person X. So your physical ontologies should all be extracted from that for different application use cases from that common logical framework, which is what probably most of us have been thinking about as being the kind of ontology that we think is an ontology of things in the world. But we've made these data typing and data surrogation decisions in order to derive that from our pure model of real things. So to give you a little example of how that might work, let's go back to that question of what happens when I suddenly stick data into my original OWL serialization of the DL model. So the description logic directly represents a bunch of things in the world, or strictly speaking, our conceptualization of what we believe exists, because we don't really know the world, we only know our appreciation of it through conceptualizations. So the serialization of the OWL model obviously represents the same things. It's not a model of data. You're going to derive this logical level ontology for your enterprise knowledge graph or other triple stores and things. What happens if I suddenly stick data into that? It's like I've thrown a little switch now. It's like a little relay where the moment I touch the third rail and put RDF instance data into that OWL model, and I'm saying instance data here, not individuals, quite deliberately. People say, oh no, you have to say individuals in OWL, it's not instance data. Well, it jolly well is. So what you've immediately created there is digital twins of the things in reality. And because of the open world, you need not necessarily have data for that. But would you ever want to use this? More likely you'd want to have an ontology that gives you instance data with data types and digital fingerprints and so on, that can work on the available data and that keeps the data folks happy and does a useful job. So I'll probably skip over this one, but just very briefly, perhaps, you have this idea of T box and A box. So the things the data is about is the A box, and the T box is the data focused extensions of those. And those may have more or less distance, what I call a data delta, between that and the intentional descriptions, the intentions of the real things in the world, following a kind of semiotic triangle adapted here into a separation of intention and extension of the real things. You can reduce that data delta, but it never quite goes to zero, I don't think. So a couple of quick examples. In the FPML language, this is a derivatives XML schema language. You have a derivative transaction in the real world. You have two almost identical messages. This isn't the actual message, it's just a picture of some XML. One is called a trade confirmation. That has legal standing. It is part of the contract. So that XML message, as a set of XML characters and things, is a part of the real world. It's part of the legal commitment, just as a paper contract would be. The almost identical report has just a difference in the heading saying this is a trade report. It's for you to tell some regulator or somebody else that I did that trade. So here we're confirming I'm doing that thing, and here we're reporting about it. So the aboutness is the key. In the world of data, the trade report is a schema with information about some derivative transaction. In the real world, the almost identical trade confirmation message has legal effect. Typically, there's a thing in a broader agreement called a covering agreement that says this kind of message will be construed as your confirmation of the commitments you're making in the world of real law. So they almost look identical, but one's data, one's real thing. So with that in mind, we have our different kinds of ontology to reflect the different commitments, real world versus things in data, commitments to different data decisions, different typing schemes. And now we can think about how we use that. Are we doing a semantic technology application? Are we doing data integration? So that little thing I mentioned about not being able to use all the data types should be a clue that you maybe want a different kind of data-facing ontology for data integration. You may need ontological representations of the typing schemes that you're mapping between. What about people? You may want to align, say, for example, after mergers and acquisitions, you have two different companies have different conceptualizations of the world. You may simply be aligning the way that meaning is thought about between people, or how the meaning as management and management reports and dashboards and legal reporting and so on describes its world, and does your data even reflect that? So there's all of that. And then, of course, you've got things like AI and explainable AI, where you really want to model the real things in the world in order to talk about them. So there'll be different design guidelines for each of these. I won't spend much time on this bit, I don't think, but one of the design guidelines I mentioned in the earlier slide was having a deep set of classifications versus having a more localized map of relations among things that are internally mutually consistent and provide a mutually consistent, meaningful representation of something suitable for an application, versus these high-level abstractions, which people will rightly complain about if they show up in an operational ontology, which are absolutely needed to separate and disambiguate between kinds of things across a business or an organization and so on. And those foundational ontologies of the deep abstraction give you these kind of bit like you've got sight and sound and smell and so on coming into a human brain. You have these sense inputs for a business of logistics and contracts and money and law and so on. So you've got ontology, you've got your concept ontology, you've got your application ontology. Sometimes you use words like reference ontology. So I separate out what we call it by its purpose, like reference ontology, versus its style, its internal nature, so those 3 dimensions of the model. So you can use a concept ontology as the kind of ontology you'd use for the purpose of a reference ontology. For an application, you'd have a use case. To be something that has a use case is to be an application. A concept ontology does not have a use case. It is the same kind of thing as a use case in that it is a computationally independent model, and it has a business use, which is to be that computationally independent model. But an application use case will have some kind of, for an application ontology, will have some kind of use case. But we may even want to split those down. It's not necessarily the case that every application ontology can be used for every job. What we might use for mapping will be more like a conceptual ontology, but with operational data types. What we use for reasoning may be a lot simpler. It may be structured very differently and so on. And so for those foundational ontologies, you need top-level ontologies, something we talked about on some of these sessions. You need those kind of abstractions. You don't need them for operational ontologies. In an operational ontology, or even in a set of reusable ontologies like Fiber, you may use localized design patterns, ontology design patterns, in place of an upper ontology. The upper ontology does the same thing. It sets out common partitioning like relative or contextually defined things, temporality, events and processes, and all those kind of things in order to disambiguate across quite a wide space. And then in selecting your upper ontology, there's a bunch of things to think about. For example, there's BFO, which is a very well-known upper ontology, but it is locked into realism, and so it may be completely wrong for anything that requires conceptualization of design or risk or business commitments or anything like that, but completely right for something that might involve physics or something like that. You've got the 3-dimensional, or sometimes what we call 3-dimensional plus versus 4D ontologies, like the ideas ontology framework. Ideas also has intentional versus extensional. What it's really a model of is what you know. So it's a very different kind of thing from a conceptual ontology or a realist ontology that's sort of conceptual but doesn't like the idea of concept. So there's all sorts of, and none of these are right or wrong. They're right or wrong for a particular job you're trying to do. Some of them rather unfortunately don't allow multiple inheritance, which feels like a mistake, but that's their choice. Whereas if you've got a high level of abstractions, you often want to intersect things so that, for example, a whale is both a marine animal and a mammal. And so you have different ways of classifying things for different purposes. Your conceptual ontology will typically have lots of different classification facets. You know, going back to derivatives, you might have, you know, swaps and options and forwards and all sorts of things you've never heard of, or you might have commodities derivatives, foreign exchange, etc. There's always different ways of classifying things, and that goes right the way up to the top of your model. You want to say something is both a physical thing and a so both a relative thing and a continuant thing, or it's relative and a current, or whatever. And it's good to have support for common patterns. There's some, as I mentioned before, you either have ontology design patterns within an application ontology, or a foundational ontology that defines the most semantically primitive kinds of things like contracts and agreements, products, and so on. I've misspelled, it's not archetypes, it's archetypes. Something like a stereotype, I often informally use the word archetype, say what is the simplest kind of thing that's a contract, what's the simplest kind of thing that is a legal person, and so on. In other words, what is the broadest set of things that has the necessary and sufficient conditions for membership of that kind of thing. And in some languages, we're starting to see now, like GUFO in particular, that's derived from the Onto UML and UFO framework, you have the idea of something that works like a domain-specific language, except it's not domain-specific, where you can start to identify, and once the tooling comes along, start to drag and drop common archetypes. So I've got a contract, and I've got a transaction, and I've got a party, and I've got a legal person, and I've got a company. And I drag them onto the page, and ideally they bring in their rules instead of having to have lots of locally enforced rules or shapes or patterns or shackle shapes or something. You inherit those characteristics from those simplest possible archetypes. Operationally, you don't want to do that. You want to have ontology design patterns. If you're deriving operational ontology from a conceptual ontology, you may simply want to bring in what would have been the inherited common characteristics. So you have patterns. Fiber does this, for example, instead of having the relative things upper ontology partition, it has what they call a 3-part or 5-part pattern for things like ownership and control and those kind of relationships. And there's the events ontology design pattern from, I think it's from Pearl. It's one that I've often seen hanging around that's very useful. Here's an event, it has a time and a place and so on. So that's it really. Some of that was a bit more detail than I remembered I promised you. I've got an annex showing some popular upper ontologies, but I don't intend to spend time on that. That's just a takeaway. It probably hasn't done justice to most of them, but it just gives you a sense of what kinds of ontologies are out there and the different styling and things that requirements they meet and so on to do that. I tend to use just the top slice of SOA, so the independent, relative, and mediating, concrete and abstract, although I think there you probably want something like physical information and energy or something like that, and continuant and occurrence, so you can have ontological models of events, processes, life cycles, and so on. You don't have to limit the ontology to just the things that stick around. And this is what we used in the early Fiber conceptual framework, and in a community called the Semantic Shed, we've been extending and refining that as well. We don't use the rest of, we call it a lattice because the original SOA thing is like this, all this form prehension nexus stuff. We don't bother with that. We just give everything a parent from one of each of these 3 top slices of that. So that's some of the upper ontology stuff. The rest of the takeaway. I'll stop there for questions and comments and things. Assuming you're all still there.
Yes, thank you, Michael. Michael, there are several questions in the chat. I realize you haven't had time to look at them, but let's see if we go back to the beginning here. Starting with Ravi, he asks, would it require what would it require to mature to an information model rather than data model?
Oh, good question. I think before you do that, you've got to define your terms. Yeah, I like the idea of having, modeling information. Well, one of the things I mentioned briefly in the partitioning there that I think is really important is to recognize the need to model information as a thing. Now, I like the idea from Claude Shannon and others of the most broadest sort of archetypal notion of what is information is simply this non-randomness, and then we can talk about human information like words and pictures and noises and so on. It's certainly, I think, for most practical ontologies, it's important to have an information partition. Within that, if you're really ambitious, you could actually start to model your data as a thing, your data types. You would need that for things like a typing scheme for mapping across different kinds of data. So that's where I would start, Ravi, is I would start by identifying those real things that are information, either as classes of things or as classes you need to refer to in the truth makers for other classes of things as information. And that's your information model. And then deriving a data model from that is a simple matter of selecting your typing scheme and going ahead with it. You could even take some of the tool frameworks like Cameo Concept Model that will let you have a DL model in the same tool as you have logical and physical database design models, and you can start to connect some of that together, possibly even generate stuff, but certainly have trace linkages between them.
Okay, and then after that, I had a question, Michael. It's earlier on in your slides, you were talking about the data and conflicts that can exist between your conceptual model and the data. So there's a couple of aspects of that I had questions about. One, are you assuming that some representation or existence of data exists a priori to your conceptual model, and then you have to try and get your operational models derived from your conceptual model to conform to that existing representation?
Absolutely not.
Okay.
That's the implied assumption in a lot of how you see ontology being developed, and it's absolutely not. It's a posteriori. Once you know what it means to be things, you've got one of two things you might do. One is to look for data, and the other is to say, well, I want to create and stand up data corresponding to those things. So, for example, I might want to reason over data about some financial movements and draw inferences that are the actual legal capabilities of a bank and compare it to whether or not that thing has a banking license. So it always has to be a priori. Now, you've got a scoping question there. If you go too a priori, you end up like drawing a map of the world that's a one-to-one scale with the world. So you have a certain amount of scoping within the context that you're doing. But the idea of a computationally independent model is keep beating yourself over the top of the head and say computationally independent. It ain't nothing to do with the application. It's what I refer to when I'm building that application.
Okay, but then there's a more general question. It confused me. What do you consider data, and or what is the difference between data and information in your mind?
I like to answer that.
Oh, let Mike answer
Well,
first.
I'll answer it in my mind, because the first part of my answer is that when you said in my mind, that's really important, because there are lots of different ways that different people use the words information, knowledge, meaning, wisdom, and so on. The ones I use don't have to be the ones that you or somebody else uses. But to me, it's helpful to distinguish between information as a kind of non-randomness in the world. It might be the language acts of elephants or crows, or it might be human speech noises, or it might be writing, it might be DNA. You know, it doesn't have to be consciously produced. DNA is information. Then you have a subset of information, which is information on computers. That is where somebody has data that is stored in registers and read and written and transferred in messages and so on. So data, I find it useful to talk about data as a kind of information that is specific to computers, and information as being the broader thing. But other uses of those two words will be different. So you have to be aware of that when you're listening to somebody versus when you're speaking and using the words in what I find the most neat way of disambiguating those as separate useful concepts.
Okay, Ravi, you had wanted to respond to that question, or
Oh yes, one is a short lot of things you have covered, Mike, in your definition of data and information. To me, very simply, in the IT context or business enterprise context, let's limit to that. And within that, I see data combinations of value to business as information. This could be an example.
Right. So when you said the IT context and the business context, you tried to make it sound as though they were the same thing. But I can assure you there's lots of people in business.
No, they are not. They are not.
Exactly.
But what we do, and it brings me to your deeper questions that you asked today, and you informed us on deeper things. A real thing, a model about the real thing, and then the implementation of that real thing. These are the things you brought us early in your presentation. And I am saying that the so-called real nature itself is flexible, changeable. So if we have a digital, what you call fingerprints, conforming to reality, or the truth makers themselves are subject to change. They have life cycle, etc. So you are right, and you alluded to date timestamp, for example. That was a good example, that you can't separate the two and things like that. So I find that you presented the ontology landscape today in a complementary and different attack or approach to landscape problem than we both did, Todd, I, and our speakers earlier.
Well, thank you.
That is
Very
valuable, very valuable. But the questions still remain. For example, original debt or loan, and then their transformation into some nonsense which we did around 2007 and 8 called collective debt, CDOs, and derivatives. Now we can never transform them back to original because people's credit histories have changed, payment capacities have changed, and these single monstrous entities called CDOs caused us the market crash in
Well,
2008.
I modeled an ontology of those in great detail. We literally were walking down Wall Street showing people this model one fine Friday in September, when most people didn't know how to formally model those things. And by the time we got to the far end of Wall Street, the financial crash had happened, and suddenly the next week everybody wanted to know what CDO squared and CDS and all the rest of it was about. Our ontology defined the legal commitments between people, and one of the interesting issues was that if you create a pool of a bunch of loans, the typical securities data doesn't have somewhere to put the data you want to penetrate through from the pool to the individual loans, or even some of the pool characteristics like locations of the real estate used as collateral and so on. So existing data models are very rigid and very context specific, and suddenly the world needed to be able to penetrate through from what was a security to what was a loan when they were in completely different data silos. And it took them many weeks to unpack that because they hadn't got an ontology.
Very good, Mike. So since we have that example that you just described, let us think of entities changing. Since we are talking of ontologies and also sometimes talking of knowledge graphs related to them, as ontologies will change in time, EKG could be a model of that. So the truth makers will change.
Yes.
How will there be corresponding digital fingerprints changing in that situation? Isn't that an interesting question?
It's a very good question, and it relates partly to the kind of Kantian distinction I was alluding to earlier, where we never quite know the world, we only know our perception of the world. And what we're doing with data in organizations is parallel to what we do in our own brains when we create a model of the world. That model is never quite the world itself. We only know the world through our models. And the more detail there is in our models, the more flexible they are in helping us understand the world. And one of the challenges, although not the only one, is how everything always changes over time. So your conceptual ontology may have a lot of stuff about time and temporality and past and present and future tenses and so on. In data, of course, there's no such thing as the present, but conceptually there is. Conceptually, we have instants, for example, whereas in the world of physics, there's no such thing as an instant. So we've got to have this very nuanced way of capturing the ways in which we conceptualize the world, and you've got to really want to abstract from that for anything that changes over time, which is basically everything, in order to have ontologies relevant to a particular context in which you're carrying out particular activities for particular competency questions or use cases, where you never want all of that complexity in any one application.
Okay, Ravi, let me ask another question from one of our participants. Ravi?
Before I go off, I will say that there is Robert Rovito and others have asked questions on the chat.
Yeah, so I have to go at 1 o'clock.
You are probably doing the same thing, Todd.
Michael? Okay, yes, we have a couple of minutes left. Pete Rivet asked a very specific question. How would you associate data surrogates or fingerprints to classes in an ontology?
Good.
Right, good question. I think for a lot of it, it's where you're defining your main class of interest, like say a security or a legal person or something, or an institution, and you have various properties, and each of those properties needs to refer to something. In the world of data, a lot of those properties refer to some data, so it could be text or a number or something. So a lot of the sort of digital fingerprints are what you need as the range of a possible property. So for example, you may have a property for name that is simply has name some text, and that's all you ever need for your name property. But the real thing that's a name is something more fundamentally conceptual. It's how I know myself, and it has parts to it about different ways of how I know myself and so on. So that's kind of an example. I think, Pete, it would mostly be the kinds of things that are going to be at the far end of the property.
How do you distinguish which properties constitute part of the signature as opposed to properties which aren't differentiate, for example?
Yeah, that's the key thing, is the differentiate, because in theory, when you're breaking down your hierarchy of kinds of thing, every single new property could be defined as another class of thing defined by just that property. In practice, we never want to do that. So we'll typically have, say, a new class called security that's a child of written contract, for example, or transferable contract, whatever it happens to be. And you may introduce 5 or 6 new properties in that. Now, in a data model, you'd often have fewer classes and lots of optional properties, because you're not using that data model to tell you what it means to be that thing. In a pure conceptual ontology, you're trying to say, what does it mean to be this class of thing? What are the necessary and sufficient conditions for class membership? So out of the 5 or 6 new properties you may have introduced there may be only 1 or there may be 2. And it really is about, what does it mean to be that thing? You may need to go back to your subject matter experts or consult some book of law or physics or whatever the thing is that makes it that thing, and find what are the properties, the characteristics that, if you remove one of those properties, the thing you're looking at is not a member of that class of thing.
So I understand that's the point of it, but how would you record that decision? Have you developed, or are you aware of anyone who's developed some sort of annotation to say this property is such a property when associated with this class?
No, and that's a really good idea, because even without thinking about the data digital surrogates thing, just being able to annotate, this is a necessary and sufficient condition, this is a necessary condition, this is a sufficient condition. I've not seen good metadata. I know Cameo Concept Modeler has some stuff around that they annotate in the diagrams and things, but that would be a great area to see some decent metadata even before we think about the data surrogates for those things.
Okay. Well, thank you, Pete. Thank you very much, Michael, for your very interesting presentation. I hope we'll be able to share your slides with the participants today and everyone else.
Yes, you will. I've got another meeting for an hour and then I'll send them. So
okay, so you'll send them to Kenneth and he will post them for us?
Sure.
Okay. So now I want to let everyone know that next week we're going to have Claudio Mazzello speaking on his experiences, in particular with using Dolce, and about a pluralist view of reference and foundational ontologies. And here's a bit of information about Claudio, if you're not familiar with him. So again, on 10 March, we will have another presentation for track A. And then on 21 April, Mike Oshold from Semantic Arts will give us a presentation for track A. So thank you, everyone. Have fun out there.
Thank you, Todd, and request Mike to look at the chat board and see if there are some questions that you can email.
I will do that later. Thank you, Ravi. Thanks, Todd. Thanks, Ken.
Surely. Thanks a lot.
Take care. Bye.